as you can hear our little voice there saying we're recording the session here. And what we will do is we'll upload those recordings to the drive and onto YouTube and that later on if you want to have a review some of the stuff on here. So without any further ado, okay, I've already gone through that. So just very, very quickly, we're going to go through just some of the main inquiry questions. Now, the intent of the course is for you guys to develop your own scientific inquiry, essentially to work like scientists. And so there's 4 modules, but there's also a couple of little things there as well. So the main assessment item in the course is your scientific research project. And so you've got 2 aspects to this. You've got journaling your process and you've got reporting on your process. So that is your report. The main thing as well is that you have to journal what you're doing along the way. Essentially, you're keeping a diary. Now, what I've done with my students is we use a digital diary, and that means that we can keep on top of things a little bit easier. And when I marked some stuff to do with their digital portfolio earlier this week, it was easy for me to go through and have a look at that stuff there. So that's the final product. That's not one of the actual sort of things that the subject stuff that's in there. Now, one of the things here is part of your report, you have to do all these little things here. And look, it's just big meta language that is covered through all of this other stuff as well. But what we need to do is, sorry, I'm just letting people in at the same time, is that one of the things that you're doing is journaling what you're doing, and then you're doing your report. And so when you're doing the scientific report, it's something that's a little bit different to what you're probably used to doing in the past. It's actually, in this course, we take the actual structure of a proper scientific report, and you have to do it that way. I know in the 2-unit courses in my school, we're actually taking this same framework here. So all the science stuff we do is becoming more scientific, if you want to put it that way. Now, of course, this is going back a little bit here, the modules of scientific, the foundations of scientific thinking. And this is where most of you probably would have started. And what we're doing here is we're having a quick overview of how science works, or how science has got to the point it is here. And so there's this idea, the development of modern science. And it's an interesting thing to, when you sort of look back at the history of science, the idea that up until the 1700s, science wasn't actually a thing. It was often referred to as natural philosophy and things like that. It's sort of only post-Newton, really, that we've got this idea of science being a thing. And if you look in the life of Newton, he was a very interesting man, and he was also an alchemist. He was trying to find gold from lead and stuff like that as well. But if you look at the inquiry question, we're talking about philosophical arguments. And so science has a lot of meta language, it has a lot of processes, but in the end, it's all about trying to find the truth. Now, one of the first things we talk about is this idea of epistemology. And epistemology is just a really fancy way of saying, how do we know what we know? And it does have it's a little bit of a weird thing here, talking about the development of navigation. And I think the reason that was thrown into the course is because navigation is probably one of the big things that took people from just living in their local village to going places there. And of course, one of the things there, we look at it, the first boats stay close to shorelines. And what we regard as sort of the beginnings of civilization is all in the Middle East. It's sort of essentially where Iran, Iraq, and that are now. And so I think it was Mesopotamia at the time. And so a lot of that early navigation was around the western part of that, around where You've got Israel, Lebanon, and places like that at the moment going around the Mediterranean. And so another thing that happened with navigation is that knowledge of the sky was really important. A lot of the early sailors would only sail at night because they knew where the stars were, and they knew if they could follow where the stars were pointing, they'd be able to get somewhere. They also used things like sounding weights. And a sounding weight is essentially just a big blob, big heavy blob on a string that could tell you how deep you were. Then around 1000 BC, so we're talking 3000 years ago, navigation charts, maps. And so these were pretty much sort of around that Middle Eastern part there, around the Mediterranean. So you had Greece, the Greek civilizations, the following on from the Egyptians, and we started developing maps and charts. Oh, sorry, Palestine, is that? Thanks for that, Batul. You also have an interesting little thing I like to throw in this Antikythera mechanism, which is something that was found around 100, thought to date to about 100 BC. And it's this little thing that found at the bottom of the Mediterranean, which appears to be a navigation device. And around that time was probably as you're probably talking about the Romans, about 100 BC. So there was some interesting stuff going there. In China, it's thought that about this time the compass was invented. And of course, one of the things is, if you look in the history books, a lot of our history that we read about is written from a Western perspective. But you go to the Eastern countries, China, India at this time as well was doing a lot of stuff on that. And we'll actually discuss that a little bit later on. You also have a little thing here, Kamal, which is a little device used to work out latitude. So when we talk about stuff there, particularly if you're looking at conspiracy theory, people who say the earth is flat and all that there, 100 BC, the ancient Greeks, the ancient Egyptians, everyone knew the earth was a sphere. And so they would use a device like this, which is the Kamal, which you could use that string, and depending on the angle of the string, you could actually work out where you were to a certain extent on the globe. Now, you also had there this as well, developed from that was the sextant. And the sextant is something that I think is still used on most modern ships. I am pretty sure that most modern ships, the captain still has to be able to use the sextant and still has to be able to work these things, just in case things like the GPS systems go out and stuff like that. But these are all devices, and these are all things that show how scientific thinking has developed. You have the Kamal, which is just a bit of wood with a string on it. And then from there, you're able to develop the sextant, which is quite a complex bit of machinery for people to use. Now, of course, the word epistemology just means a theory of knowledge. How do we know what we know? How do we go about knowing what we know? And the idea is that it's different to belief and opinion. So, and unfortunately, in the modern world at the moment, the difference between opinion and knowledge is kind of a little bit of eroding there in this sort of post-truth Trumpian world. And essentially, epistemology is how do you go about knowing what you know, and how do you know that what you know is actually true? A lot of circular logic there, unfortunately. But what we can also look at there is that there is this history of how things change. This modern idea of epistemology, this idea of science, does go back to people like Plato and Aristotle in the Greek world. And you then have this huge bit of a gap to go to the Middle Ages, and you had people there. And then it is a huge gap to this modern idea of thinking. If you look up these people, Descartes, Spinoza, John Locke, and all that, there's some really interesting things there, particularly talking about philosophy and this idea. How is it that we know exactly what we know? And look, I gotta admit, if you go down the path of looking at those things, there is just a whole range of stuff. Now, it's way outside the scope of the course, so we won't go into too much there. But of course, everything in the end is all about finding this idea of what the truth is. At the end, most of the time when we start teaching you in year 7, we say stuff like, science is an organized approach to learning. And in the end, again, science is about finding the truth, finding what is real. And so you have this idea of what is truth. So this idea, oh, it's true. It's state of being true. It's often really hard to make judgments or make comments about things by using the word that you're trying to define. So what we basically say there, I do like the middle one there more than the other ones, the idea of something that's factual, something that's reality. So it's something science is trying to find what reality is. And of course, reality is sometimes a little bit hard to actually work out what is going on there. Now, you also have related to that empiricism. And empiricism is a really important thing, because to know the truth about something, you need to actually have knowledge behind that. And so in terms of what is going on with empiricism, is this idea that you can only understand something when you relate it to other things around you. So the example I often use for this is talking about atomic theory. Now, you can understand atomic theory, and we start off with, we always talk to you in, say, year 7 about, well, there's atoms, and atoms are the smallest things. Then we get to year 8 and we say, well, they're not really the smallest things. There's protons, there's neutrons, there's electrons. And then you get to year 9 and say, well, okay, these things sort of interact with each other. And then we get to year 10 and say, well, sometimes they break apart and they do this. And then by the time you get to year 12 physics, we also say, well, they're not really things. They're kind of fuzzy little things that kind of exist. And if you go further than that, you can say, well, matter's possibly made of strings and all this here. If we just taught you that quantum mechanics, although you could argue that quantum mechanics start there, a lot of people wouldn't understand it. They can only understand it because they understand the basic things. And so in a lot of ways, their experience comes from things like, is where scientific modeling is really important. And the idea that you can understand something because you understand simpler concepts there. And it's the same thing that we do as human beings. You learn to speak and you learn language by learning basics, and you build that up, and then you can then understand the more complex words as you get older there. Now, we also have a couple of little things here, inductive and deductive reasoning. And these are really important because essentially the scientific process and the idea of finding out the truth is based on this. Sometimes we're trying to find broad knowledge, sometimes we're finding very specific knowledge. And so when it comes here, what we do is in induction. Induction is you find a general rule and you basically then apply it. So in a lot of the statistical stuff you might look at, you might say, well, we looked at this here and 10% of the people we tested have a cold. And then your induction then is saying, well, this way, then 10% of the entire population must have a cold. It's a sort of thing there. So you got the premises there. Humans exist, birds exist, therefore birds are human. Now, what you've got here, inductive reasoning is, you can probably argue it's not the most scientific thing here. You can have premises that are true, but your conclusion is false. And I suppose that's a bit of the human existence, or the human thinking, trying to apply things there. You also have deduction. And deduction is that we apply general rules to particular cases. And so we're looking things a little bit specifically here. And so this one here, as I said there, Aristotle, one of the early Greek philosophers, sort of looked at it here. He said, all men are mortal, so everyone's going to die. Socrates is a man, therefore Socrates is immortal. The first two statements there are premises, and you make a conclusion from that. and the conclusion is taken from those premises. And so what we are hoping there is that as long as your premises are true, then your conclusion should be true. When you look back at induction, you can have premises that are true, but you can make a false conclusion. And so it's a tricky little argument there, but it's something just to keep in the back of your head. And, as and I think I've just explained that there, this idea there, deductive reasoning is top-down logic, is that you're sort of looking at big things and looking down, and induction is little things and going out. Inductive reasoning has its problems because it still is used in science. If you go back to the Andrew Wakefield MMR controversy, that was a case of inductive reasoning that was wrong, where he sort of looked at 12 children and said, well, these 12 children prove that MMR vaccines cause autism, which was completely a false. His premises were reasonably correct, but his conclusion from that was completely wrong and out of there. You also have this idea of parsimony, and we're talking about parsimony and Occam's razor. And so the idea that when we are looking at a scientific idea, or we're looking at any idea, and we're trying to work out a conclusion from it, the idea is that usually the simplest thing or the simplest explanation is usually the most correct one. Pardon me. If you look at other things here, now this is usually called Occam's razor, coming from, I think Occam was an ancient Greek philosopher as well, if I remember correctly. The simplest things are always the most logical and the most likely to be the explanation. So if we look here, there's a couple of examples, and look, these are actually quite, they're kind of ridiculous examples, but they highlight the process. And so, the one here, man sending his wife text messages. And so 2 explanations: her phone ran out of battery, or she's maliciously ignoring him in revenge for something there. Now, I'm not going to make any misogynistic comments about depending on there, but the most likely explanation is probably A, unless you had a fight earlier that day, and then maybe B. One there, the second one, a woman is nauseous, so sick after eating at a restaurant. So she could have food poisoning, or her long dormant fetal twin has awakened. Now that's quite a ridiculous one there, because food poisoning there, but there could be other explanations. She could have some underlying health condition or something like that. Now, as we move from those ideas of reasoning, Occam's razor, and that there, we get to this term that's essentially, you can be quite easily argued, falsifiability is what modern science is built on. It's built on this idea that an idea can only be scientific if it can be proven wrong. And so in this case here, it's an example of 2 wrongs almost meaning a right. So Karl Popper, or I think it was early in the 21st century he was working. And so the idea is a scientific idea. So we use F is equal to ma, Newton's second law. The force applied, or it's better to say that the A is force over mass. And so to accelerate an object, you apply a force to a mass. Now, with falsifiability, if you can prove it wrong, then it's scientific. It's a very big distinction between scientific ideas and faith-based ideas, or ideas based on belief. So the idea that, well, I believe this is the case, it's not a scientific idea unless you can actually prove it one way or the other. And this is kind of a hard concept, I think, because it's sort of almost a negative thinking process. Now you also have, and this is a really important concept in the modern world, this idea of confirmation bias. And so the idea is, this cartoon here, everyone seeks confirmation bias. I knew it. And then the guy realizing, just wait, that's a form of confirmation bias. And the idea of confirmation bias is that in science, you can do research, and as you guys would all know, you go through any scientific process, you do an observation, develop an inquiry question, you make a hypothesis. Confirmation bias is where you design an experiment that's only going to prove your hypothesis right. It's got no chance of proving it wrong. And so confirmation bias means that often you will look for results that confirm your original hypothesis. And that's kind of a dangerous thing, because that's where you get processes where drug companies will only look at the good benefits of a drug and not look at the side effects. And, there's a whole argument going on at the moment about vaccines, and, whether the probability of getting a blood clot from the AstraZeneca vaccine, which is infinitesimally small, but, that might have been a thing that early on, well, I suppose the vaccines were developed so quickly that no one had really noticed that until it was in the field. But it happens in other things there, particularly when you're talking about vitamin supplements and things like that, which claim to be scientifically tested, but they're probably only looking at the good results. Now, of course, one of the things there, this is really important because confirmation bias, it pretty much runs our modern world. Online social media stuff, particularly Facebook, is probably the worst for this. Is that if you are on Facebook, you'll notice that most of the time you get stuff thrown at you. They've got algorithms that actually look at your search results. So if you've ever had Facebook on your computer, and even if you've unlogged and done all that crap there, there's still little bits of code in the background, little bit cookies and stuff are there that look at things like your Google searches. And then what they do is they use that to try and give you more content that relates to what it thinks you are interested in. If you click on videos on Facebook, that gets added to your algorithm. And I think, unfortunately, Facebook can probably tell you your personality better than anyone else can. Now, all of this stuff here that we've just been talking about there leads up to this idea that the theory dependence of observation. And this is it's quite an intuitive thing there, that you can only understand something if you've got some knowledge of what that thing might be. And so there's this little example here. Now, most of you are going to look at that and say, okay, that's a duck. Now, it's a stylized picture of a duck. It's a cartoon style duck. And the only reason you could say that is because you have some knowledge of what ducks are. A duck is an aquatic animal or aquatic bird. It has sort of a bill type thing here. It's got eyes, it's got wings. When it's drawn like this, it kind of looks cute. Now, yes, it is, Angus, because when I press the next button, I say, well, maybe it's not a duck, maybe it's a rabbit. Now, again, you can say, well, okay, that's a rabbit because I can see it's got its cute little bunny face, it's got its cute little bunny ears, a bunny tail, its bunny legs there. And this is an illusion, but it's also the fact that for you to understand this illusion, you, one, have to have some sort of knowledge of ducks. Two, you need to have a knowledge of rabbits. And, you need to not to freak out too much when this goes that there. But this is a really good demonstration that you can only understand this illusion if you've got a knowledge of what a duck and a rabbit is. You show this to someone, probably more toddlers, who have no idea of what those animals are, or someone who's never been exposed to those animals, it's just going to be a picture. It's not something that they can do there. And so this is a really important concept, because for you to understand science and you to understand complex science, you need to understand the basic science. And that's why we teach things like the atomic model at a very basic level and build it up, because it's very hard to understand the advanced stuff unless you really understand the basics. Now, that is a sort of a little bit of a background to what our philosophical approach to science is. Science is about applying rules. It's about using logic to find the truth. And it's about building up knowledge. Now, one of the things that often gets misrepresented is this idea of ancient knowledge. And particularly, as I had mentioned earlier, we're sort of in a Western culture. So we've got this Western idea of what science and what knowledge is, taught from this sort of classical Anglo idea that all the great knowledge came out of Europe, particularly the Greek civilizations, and there wasn't much else going anywhere else, which of course is a very biased sort of thing there, but it's what it's classically been taught at. But there's plenty of other cultures there. And of course, if you read the news, there is a bit of controversy about things like Indigenous culture and that there. But, you know, there is Indigenous culture. There is Indigenous knowledge. There was Indigenous knowledge that's been applied in a scientific way. Now, it's not necessarily applied in what we'd say a classical scientific method is, but it has been done there. And so a couple of little things here. The idea that the idea of astronomy and understanding the stars has popped up in every civilization. It's popped up in South American cultures, popped up in the African and the North African cultures and the European cultures. I don't know much about the North American Indians and Inuits, but they've probably got that astronomy idea there as well. Now, the one thing that didn't really happen in the Indigenous Australia groups that may have happened in other ones is that there was no real written language developed. And so this is why a lot of the Indigenous ideas come down in oral traditions. And so the idea of stories, dance, ceremonies there, and they're used to explain the natural world. And so the one here is this idea of the emu in the sky. And so there's a whole story behind it. And so what you get there is, you know, the emu, which is essentially, I think that's part of the Milky Way, which if you go out where there's no light pollution, you can see all these fantastic constellations. But if that emu was at a certain place, Indigenous people knew how to, gather food, or it's going to get cold, or it's going to get hot. There's a whole range of things going on there. And so because Indigenous people didn't really develop a written language, stories, dances, songs are a way of passing that down. If you've ever tried to do memorizing techniques, one of the way people are able to memorize things better is if you attach a story to it. And so in this case here, while we sort of talk about dreaming stories, they were a way of passing down actual information. Because if you just said, well, if that cloud there is over that rock there, then start gathering food, that's not as easy to remember as a story. Also, things there. So Indigenous people did use stuff like, so spinifex grass is used as a glue. There's also a whole other little things there. You also had, and this is probably the biggest and probably one of the more important Indigenous bits of knowledge that have come about in the last decade or so, the idea of fire stick farming and traditional farming methods. One of the things that's happened in the last 20 years is that some of the bushfires in Australia have been absolutely huge. And that's because over 50, 60, however many tens of thousands of years, Indigenous people would basically clear out the land. They would go through and they would do brush fires through certain areas. And that knowledge is still being passed down now. And it's actually something that forestry commissioners and stuff like that are trying to take on board, because the Australian bush over those tens of thousands of years slowly evolved to actually need fire. Most of the Australian plants actually need fire to germinate. They need fire to grow. It's such an important part of the local ecosystem, and that when Westerners came in and said, well, no, we're going to keep that forest the way it is, those forests become really, really, well, they become very flammable very quickly. And so this was a thing used by Indigenous people. One, it kept the area clean. It was you're able to move around a lot better. It also meant that if there was new plants growing in the area, then animals would flood in. You could also use fire to corral animals and hunt and gather and that there as well. You also have there that one of the things that when you've lived in Australia long enough, you realize that the four seasons, which are a very European idea, summer, spring, winter, autumn, they don't work well in Australia, and particularly in the northern. If anyone's ever been to the northern parts of Australia, particularly around Kakadu and stuff like that, the idea that you have two seasons. It's either wet or it's dry. It's still very, very hot. And so some things, I think around the Sydney region, a lot of the Indigenous people had 6 or 8 seasons. Now, of course, these seasonal things with the moving of seasons due to climate change and that there would have to be readmitted. But again, these were delivered in stories and songs and things like that. Now, what we go here to now, ancient Greece. And so ancient Greece is in that, as I said before, in that Western tradition, is where most of what we think science has come from there. Now, we do that because essentially Greeks did formulate a lot of really good stuff. They formulated numbers, the modern number system as we know it as well. A lot of our modern mathematics stuff here. So, in mathematics, you still get taught Euclidean geometry. The one thing I think that the Greeks did really well that probably other civilizations didn't necessarily do as well was producing it all in books and producing it all in there. And I suppose it's also the fact that those books, for the most, a lot of them did survive through a lot of different things there as well. Also, astronomy. Astronomy is something that's the Greeks are able to apply their skills very well there. They were the first ones to come up with some ideas of how the planets moved around. And, some of the ancient Greeks' ideas were, well, some of these are planets, some of these are other things there. I think it was, and someone can correct me here, there was either Democritus or Aristotle actually came up with the idea that the sun was the center of the earth. It was just that the Greek philosophy of arguing was eventually they sort of argued and said, well, the earth's probably the center. They also came up with a lot of medical treatments there. And again, all Western doctors do this thing when they become proper doctors, whatever that is. Okay, thanks, Ian. It might have been Aristarchus. As I said, I didn't have it on the top of my head. Actually, and now that you've mentioned that, there it probably was Aristarchus that came up with the heliocentric model. But yeah, he was laughed at because it was, the philosophers thought that was silly. I'm just going to agree with Plato. But Hippocrates came up with this idea of medical treatments and this idea of studying symptoms. Now, you've got to realize before this point here, and it was still so well held around the world, that sickness was basically about demons. And so Hippocrates looked at it there and said, well, no, this person's sick because they've got this bug, they've got this here. And if they've got this sickness, if we treat them this way, they'll get better. And it's not just about praying around someone and hoping they're going to get better. As I said before, the Hippocratic Oath is this idea of medical doctors now. And the idea of medical doctoring is that I think the Hippocratic Oath, when you translate it, means do no harm. Okay, so the idea is that you don't treat someone, you try not to make them worse, which is unfortunate in some cases. They also studied the world around them. So, the early study of biology and zoology, classifying plants, classifying animals and things like that. They tried to sort of look at those relations between those. And of course, there were some inventions that can still come around now. One of the things there, the early think of a water mill for grinding grain. So at the time, grain there, you either had to sit there on a rock and grind it all together there, but they came up with this method using a water mill. Plato also came up with a water clock to wake himself up in the morning. Things like central heating, which is basically hot air going around the house, and a whole range of things there as well. And of course, the ancient Greeks we give a lot of kudos to, but also there was a lot of stuff happening in places like ancient Egypt. We credit the ancient Egyptians for coming up with the first kind of form of written writing. They're also the first people to come up with a type of paper that could be used. And so, it was important, particularly because Egypt was one of the first places where things like commerce, business was becoming really, really important. And it's like, if, I want to pay 10 shekels to Ahmed for him to do a job for me, well, you need something to write down to do that. And so essentially writing was designed to sort of keep business there. But of course, at the same time as well, the Egyptians then started doing things like storytelling and things like that. And that eventual hieroglyphic text eventually became more stylized and became some of the letters and numbers we got there as well. They also had some medicine as well. A few of them were a bit strange there. If you've ever watched TV shows like Horrible Histories, they look at some of the things there. If you've got an eye infection, use a bit of honey in someone's brain. The whole cooked mouse to cure your cough. I think it's more the fact that it's just so gross that it's doing there. But I think ancient Egypt also had some early surgery type things there where even though they were still thinking that demons were causing things like migraines, there have been mummies in tombs that have been found where they've done early brain surgery. One of the things there, if you know someone or you've ever had migraines, they can be quite painful. And so at the time, migraines were thought to be evil spirits. So they would actually drill into the person's skull, drill a hole in the skull, which would actually alleviate some of the pressure. It's a technique that's used in really extreme cases, but it can work. You've also got their mathematics. The one thing they didn't have there was a zero. And so they were pretty good at counting things, but they didn't have a zero. And that's something that sort of was developed, I think, a little bit later. It was developed by the Indians, which we'll talk about in a minute there. And I think it was really developed by the Greeks after that as well. You also have other civilizations would have, numbers that have one or a few or many and stuff like that. They also had makeup as well. It was more common for the men to wear dark makeup. It also had a bit of an effect, apparently. It would work like really bad sunglasses to get a little bit of protect your skin and a little bit there. They also had toothpaste, and the idea there is that Egyptians worked out that their bread had a whole heap of crap in it, so they invented the toothpaste. And if you worry about the taste of toothpaste now, think about it. You might have had ash, eggshells, ground up ox hooves, just any grit in there, and you wash it all out. Now, one of the things here, and this is something that's sort of becoming more prominent in the last few years, is the idea of India. Now, India has such a big tradition of the same ideas we've just talked about, particularly with Egypt and Greece, but the Indians did the exact same thing. Now, one of their biggest contributions to the modern world is the idea of the zero. And zero basically made maths work a lot better. worked in so many ways. It made addition, subtraction, everything like that actually work a lot better. Now, also we had there, and the idea of Kanad, who actually, well before the ideas that we talk about atoms now, he'd actually worked out that probably atoms were these things called atoms, small indestructible particles. He also came up with an idea, sort of, they could be at rest or they could be in motion. And the idea, and this is well before John Dalton came up with the law of definitive proportions, that substances combined in specific ways. And so you've got the building blocks of chemistry there, well before the John Daltons and Thomsons and that developed that. Again, the heliocentric idea from Aryabhata, who used observations. If there are parts, if you ever go, there's parts of India where you can see a lot of the really advanced astronomical tools they used. And, he was able to make predictions on solar events well before anyone else was. But again, that's a cultural bias thing that pretty much the textbooks and everyone has. Also, I'm not sure, even though they did develop plastic surgery, I'm not sure I'd want ancient plastic surgery. One of the things there they had, they did rhinoplasty, which is essentially carving bits of your nose off. I'm not sure I'd want to do that without any things there. Yeah. Yep. Yeah, cool. Thanks, Adanga. Sorry, I missed your first point there before as well. Yeah, like there's lots of crazy things out there, and it is kind of really interesting. Like we talk about medicine and doctors and all that there, but really it's only about 104. The Florence Nightingale and the Boer War, I think, was about the 1880s. So it's only about 150 years ago that doctors refused to wash hands, because doctors at the time were thought to be people who from the upper echelons of society, and it was beneath them to wash their hands in between surgeries. Although in the Boer War, most of their surgeries were just cutting off limbs that had got infected, and that there in the Boer War, if you got infected, you're pretty much dead. Cataract surgery. Now, this is another one here, really interesting here. Cataracts in a place in a country like India, close to the equator for the most part, and parts of there where it's very bright and sunny. Cataracts are a big problem because the bright light can actually exacerbate the problem. And so, back in 6th century BC, so 2,500 years ago, they were doing cataract surgery. So, they used a needle, they basically then scraped off the stuff there, and would have been very interesting. Now, of course, those are some ancient ideas. And what we're going to focus on now is some modern ideas that really change the way people think. And so the term paradigm shift, what we're referring to is an idea that completely changes people's thinking of a scientific idea. And so we're going to, in the course, ask you to look at one of 4. So in the course, you don't have to do all of these. I usually get my students to look at all of them in brief and then do a little bit of extra research on one. So one of the ones there, Antoine Lavoisier, he was the guy who basically came up with the idea of oxygen. Prior to his research, people just thought air was just air. Lavoisier basically showed that air had other things in there. So that he discovered the law of conservation of mass, and he did that by understanding that a combustion reaction is essentially combining oxygen with something. And so it's often argued that Lavoisier is the, he's the start of modern chemistry. Prior to that, reactions are often all about, preparing gold and making gold and stuff there. I think part of the story as well is that I think his wife, there in the picture, did a lot of the stuff as well, but at the time, women weren't considered to be part of the scientific process more than anyone else. So she prepared a lot of the experiments for Antoine. One of the biggest ones, and this is one most people know about, Einstein and the theory of relativity. In year 12 physics, you study the special theory of relativity, which applies to frames of reference that aren't moving, inertial frames of reference. But probably his more important one, yes, you will, okay? But general relativity is probably the one that had the even bigger impact. Einstein's general theory of relativity essentially is that space and time aren't a separate thing. So, we often talk about space is 3 dimensions, up, down, left, right, however you want to describe it. And there's also time, which are completely separate. Einstein talks about the fact that space and time, in his general theory of relativity, are actually the same thing. And that if you consider that, then space and time can actually be distorted. Now we know from his special theory of relativity that a perception of time can be a bit different. But in general relativity, it talks about accelerating frames of references and the fact that that space and time curving has impacts on other things there. And it also led to a whole heap of other stuff there as well. And this is probably one of the latest ones. So in 1912, Alfred Wegener came up with the theory of continental drift. His idea wasn't accepted at the time. I think he died in the 1920s. So it took about 40 to 50 years after his death before his ideas were accepted. And one of the things was Wegener, I think by trade, was a biologist. And so he based a lot of his theory on a lot of the fossil evidence. So one of the things we often teach you in about year 9 is this idea that one of the big pieces of evidence for continental drift actually comes about from fossil evidence. And so this is here, South Africa, South America and Africa, they share common fossils. Africa, India, and Antarctica share common fossils. All of these Gondwana continents also have fossils of other things like Glossopteris. Australia and South Africa have very similar plants. The Waratah, and I can't remember, there's a South African plant that genetically is almost identical to the Waratah. And that shows that at some stage, those things were close together. Particularly in Antarctica, there's Antarctica on the bottom of the world, cold as, has tropical plants and animals in its fossil record. So it suggests at some stage it was in a position where it was very warm and it was a very active continent. But it wasn't until, and I think it was the magnetic, some of the magnetic stripping that the Americans were doing when they were looking at the Pacific Ocean, that sort of was able to confirm Wegener's ideas. And in biology, what we have here, Margaret McClintock discovered this idea of jumping genes. That when genetic, particularly when we're talking about sex cells coming together, that it's not necessarily, they don't recombine in the way that people would normally consider. And so, she presented some papers on this when she looked at their, people were talking about junk DNA and all sorts of stuff like that. But McClintock was able to work out that, that genes did reestablish themselves in new ways. And so explaining sort of how some mutations and that were stuff as well. as I said, you only need to know one of these examples in detail. Um, and it's not a huge amount of detail. You don't need to be able to read through every single part of it there. You just need to know more. The most important part of that is how those ideas led to new ideas in science and how they started a new, completely new line of thinking. Now, as well, we need to consider some of the influences on scientific thinking, because one of the things there, if science is trying to find the truth, unfortunately, there's cases where it doesn't find the truth as quickly as we think there. So, the idea of what currently influences. Now, it's not science, we often produces this altruistic thing that, scientists, it's all about finding the truth, but it's often not. And what we have here is one of the biggest things here is economics. The example before of Lavoisier. Lavoisier was able to do his studies because his family was rich. Up until, I'd say, even in the last 50 years, most of the people who have done science have been reasonably well off because they can afford to go to university, they can afford to continue studies. And so one of the things here, economics is really important. Now, most countries like Australia have institutions set up to try and fund science to promote it. And this is a report from a few years ago from the Office of the Chief Scientist, which is the importance of science. And particularly, this is one of the things that needs to be promoted to people like politicians who end up controlling the money, is that science actually is a benefit, not just from it's beneficial because it's good, but because it actually promotes economic growth. And so what we've got here is, 11% of economic activity in Australia at the time is thought to come directly from science. 22% of, in 2015, almost $300 billion a year was coming from scientific ideas. And that's from flow-on effects and things like that. $145 billion from science work. Almost 1 million people employed in science and mathematical areas. Exports. One of the things that we do very badly in Australia is we often come up with really good scientific ideas and then we sell them overseas. One of the things there, I think, even though Cochlear is an Australian company, I think a lot of the money still goes overseas for that. The CSIRO does a lot of research on things there, and we're quite important in the development of things like Wi-Fi and that. And, the CSIRO, I think, does get money from that, but it could actually get a lot more money from the development of Wi-Fi if it would patent it. Now, one of the things here that we are in a massive, Australia is in a massive weird state when it comes to the political aspect of science. Kind of unbelievable that we are still having, and this article's a few years old there, but Australia is still arguing whether Australian politicians are still arguing whether climate change is real. We're still, in this post-COVID world, we're still having discussions about vaccinations and things like that. 2 years ago, there was the Australian federal election. And so at the time, people were less inclined to really talk too much about climates and things like that. But things like the 2019, 2020 bushfires and the Australian response to that is mean that there is political change on what's going on with climate change and that. Also, coronavirus, the amount of money that's been poured into that there. So this is, if you go back 2015, in parts of Asia, there was MERS, which is sort of a flu-like thing. 2002, there was SARS. But last year, we had coronavirus. And what suddenly happened then is that the amount of money spent, and it basically came from governments more than anything else, on trying to find cures for that, just was exponential. And so this is where politics is able to support scientific ideas, because generally, yeah, good point there, Ian, about solar technology. I was just trying to bring in a bit of an analogy in there. But yeah, coronavirus, what have we got there? US millions. So, suddenly last year, $4 to $5 billion is spent on COVID research, because there was seen to be a need for it. And I think no one's going to argue that that wasn't a bad thing to actually do. Now, of course, global. One of the things there, and this is also relating back to what we talked there about COVID, is that COVID did promote a lot of cooperation across the world. Scientists working in different labs across everywhere were sharing information with each other. And it does seem a bit silly, but it's only in times of crisis that people actually are really good at cooperating with each other there. And so the idea of international cooperation does also relate back to politics. Now, there's a couple of really, really good examples of where international cooperation can work really, really well. And so the International Space Station, which I think was launched in 2000, had cooperation from the US, Europe, Russia were cooperating with that as well. Japan was a massive contributor to that as well. And so all these countries that in the past have warred with each other, and you can probably argue that maybe there's a low-level Cold War now with Russia as well, definitely one with China. But despite all these political differences, cultural differences, people were able to cooperate with each other. Interesting, I think it was in the last week that China have launched their own space station. Again, so we may see another space race happen in the next 10 years. And of course, all this cooperation, it's very easy to argue that it's actually quite a good thing. One of the things, we can bring in another analogy, or it's a pretty tortured analogy, but the Indian Premier League had people from different countries playing a sport commonly, and they were able to understand each person's culture a little bit better there. It's one of the things, people are often afraid of what they don't know, and if you talk to someone from a different culture, then suddenly you realize, oh, they're not that bad. One of the other biggest international corporations is the Large Hadron Collider. A lot of money coming in from lots of countries to work on some basic science. And that's something that often doesn't happen. Really hard to work out how much it costs. I think it was about $50 billion, but we can also assess the idea that, some fundamental understanding has come from that. One of the other big things as well, like when you talk about politics, economics, global cooperation, and that they all have an impact. But one of the other really important areas to work on is this idea of ethical frameworks. And ethics, more so than any time in scientific history, ethics is such an important thing. Research can't be done these days without some form of ethical consideration, particularly in biology. So when you're talking about humans, you really need to talk about the idea of informed consent. If you're doing a clinical trial, a person doing it should understand what is going on, what are the risks involved. And, there's been too many, sorry, I just lost my train of thought there. Informed consent. Essentially what we've got there is that in the past, there were a lot of trials where people weren't necessarily informed of what was happening to them. There's a whole heap of stuff, particularly in the United States, is stuff that's come to light. And if I remember correctly, I think it was the Tuskegee experiment, where some doctors basically wanted to understand what the long-term effect of sexually transmitted diseases like syphilis were. And so they offered free treatment to poor African-American people. And over 40, 50 years, they gave them fake treatments while they still had syphilis. Now, those people were not informed of the proper consent. There was also other things. I think it was the US in the 60s wanted to test the effect of radiation on human beings. So they tested it on homes for disabled kids. A lot of really bizarre stuff that's happened there. You can also go back to World War II, where the Japanese and particularly the Nazis were doing a lot of human biology tests on that, and we'll talk about those in a minute as well. Experimentation on animals. Up until about 20 years ago, pretty much everything was animal tested. In Australia, in most countries in the world, if you want to test cosmetics, you would do stuff like you would test cosmetics on things like rabbits. And so we've got this new eyeshadow. We just want to make sure it doesn't burn the eyes. So we'll put it in the eyes of rabbits. And that's a really emotive thing, because in the modern world, we sort of consider cruelty to animals isn't a good thing. But whereas in the past, it was considered normal. And you can't, to do an experiment on animals in Australia, cosmetics cannot be tested on animals. It's been banned. It did cause a problem. I think it was about 10 years ago. An Australian company, The Body Shop, wanted to sell their products in China. And China has rules that you must test things on animals before they can be sold. And so that's a cultural, economic difference between those as well. In saying that, though, there is still animal experimentation. It still is a part of the scientific process. What happens, though, is that generally it's usually mice are the main ones. Mice or rats are usually tested on, and primates as well. There is in Sydney a primate testing centre. It just doesn't get a lot of press. Although it did last year or the year before, when one of its primates was getting a vasectomy at RPA or something and escaped and was running around, I think it was Oxford Street and King's Cross. But again, just treating things humanely. And as long as basically the animals don't suffer or suffer cruelly, then generally things are fine. Now, one of the other things that's happened in the last few years is this idea of biobanks. And so in some respects there, a lot of the time is a biobank is taking biological tissue or biological data. Particularly, there's a lot of stuff that's happening, genetic testing. A lot of people want to get genetic testing to work out some of their family history. So things, I think in the US, there's one's 23andMe. There's a whole heap of things where you get a sample, you give them a sample, they sequence your DNA, and then they give you things saying you're 1% this, 10% that. One of the things that people don't realize is that when you use these testing services, there's little fine print down the bottom there that says that they reserve the right to use your genomes that they've sequenced. And so this is a really, really big thing, because if you give permission for your genome to be used, what are they going to use it for? The huge thing as well, that a lot of diseases have genetic backgrounds. So if you get a genetic test, does that mean you can be exempt from getting some insurance? Yeah. Okay, cool. Someone's gone on an excursion to a biobank. But yeah, who owns your data? Who owns what you are? And that's going to cause massive problems in the future. Yeah, so, okay, yeah, in RPA. And so you've got this biobank there. Who owns what you are? What rights do you give them? And so, who uses that data as well? So there is some risks with this as well. Now, the use of research data, if you go to a drug trial and you say, well, yeah, I give consent for this to be used, for this drug purpose here. They use that data for something else. The idea of hacking as well. There is, with the emergence of technologies like CRISPR, it's not perceived, it's perceivable in the next few years, if someone took a digital copy of your DNA sequence, that it could actually be built into an actual biological sequence. Does that mean that they can then use your DNA for criminal activity? Could it be clones? And that's in the realm of science fiction, but it's actually becoming more and more likely that those technologies will exist. Who's going to profit from your DNA? And now, as well, one of the problems in the United States in particular is that if you've sent your DNA to a DNA profiling company, there's some parts of the US where it may be possible for law enforcement to actually subpoena your DNA. So your genetic privacy may not be as good as well. But also what happens is that if a company goes bankrupt, in most countries, if a company goes bankrupt, another company could come in and actually purchase their data. And so suddenly a company that you've approved the use of your DNA for has sold it to another company. It's the same thing if you join an email list. There's usually a thing at the bottom there saying, we reserve the right to sell your details to another company. And suddenly you start getting email spam from companies offering you services. And when DNA becomes a digital artifact, who owns that? Do you actually still have legal rights over the DNA that's created you? There are codes of conduct. You've got Australia has a responsible code of conduct for research, but again, often codes of conduct aren't necessarily enforceable. And of course, one of the things here is the ethical idea as well. And this is a conversation that's been going for 70 odd years. Is it ethical to use data from studies that were bad? So the one thing there is that, as I mentioned earlier, in World War II, there was a lot of very bad experiments done, particularly on Jewish and gay and sort of basically people who didn't fit the Nazi Aryan ideal, and horrific experiments. But these experiments did show things like the limits of the human body. And so it's a really hard thing to talk about. These experiments do have good biological information, but they were conducted under very, very dubious circumstances. And who owns that? And so this is an article here from a professor of ethics. But I did read once an interview with a Holocaust survivor who said, I actually want this data to be used because I don't want my family to have died for nothing. And the idea that if someone can be helped, if some new treatment can come from the horror that happened to my family, I want that to happen. And again, it's ethics are a really hard thing because sometimes it's actually hard to say whether things are good and bad. You also have their human experimentation, where you've got this new thing here where some people are basically augmenting their body. So you may know someone who already has a pacemaker, who has some sort of medical device in their body. You may know someone, particularly something like, I think diabetes. Some people can have things like an insulin pump. How far does that go? And the ethical problem here is at what point do you not become human anymore? What point are you more machine and that there? And that is actually a real ethical dilemma that's going to pop up in the next few years, because there's pretty much every part of your body other than your brain can be replaced. And so, that sort of dystopian nightmare scenario of a brain in a jar could actually happen in the next few years. Now, that is a very, very brief outline of module 1. And that's going to take up the bulk of our time. The rest of it, we're going to go through quite quickly. And the statistics stuff, I'm going to go through very briefly, because as I said, Dr. Shamnair will discuss that with you a little bit later on. So module 2 is talking about how you start setting up your project. And so one of the things there is developing hypotheses, developing inquiry questions. And often the hardest thing in science is about your starting point. So, one of the first things a lot of you probably did is conduct a literature review. And a literature review is a really important part in the scientific process. And it's about trying to find out what people already know. So, some of you may have already done things like literature reviews and other science courses and that as well, because it's something that we're starting to throw in there. But the really important thing is, how do we know what we know? And so one of the things there, if you want to look at climate science, the Bureau of Meteorology has all its data freely available. NASA has, I think, all of its data available. This idea of open source data is becoming more predominant in thinking. But what you can do is, if you've done that, you've had a look at the data that's already known, you can then develop a research question. And this is one of the other sort of hard aspects here as well, is that trying to work out what a research question is. And there's a lot of things that you really need to take into account. Is one, if you're developing a research question, can you actually research it? You might already know the answer to something. So if you did a low level thing there, hitting people over the head makes them angry. One, that's not necessarily, there's an ethical issue there as well. But I think most of you would probably already know what the answer is. You also have there this idea of a clear focus. Sorry for that. Clear focus. Are you conducting research? So your research shouldn't necessarily be really open-ended. A good research question is very focused. And so, don't make it sort of very, there should usually be a dependent and independent variable and things like that there as well. And I'm just going to go through this quickly because you can look at this in your own time there. But what you need to do is basically be very specific. So when you are developing something like a hypothesis needs to be really specific. You need to try and explain what's going on there. So when you look at your research question, so I want to see whether all quasars observable in the universe have the same properties or something like that. I've just picked up something really random out of that there. Your hypothesis will be they will all be the same because of this, and this. Now, you've also got to evaluate whether your scientific hypothesis can actually be, whether you can actually get the data. Now, a lot of you here probably did some primary research. I know my students have tended to go to secondary research because it's a little bit harder if you're going to do a high-end thing to actually get that that primary data. But you've also got to look at whether you can get the data, whether that data is valid and reliable, and are you finding something new? Now, a lot of the outcomes that you have to do in the course are about assessing what you've done. So when it comes to your research question and hypothesis, one of the things you need to do is think about whether what you did, was it easy, and what difficulties did you encounter? So a lot of the outcomes I'm going to talk about in this little section here are about you reflecting back on what you did. So when we look at the exams later on today, or some exam questions, A lot of the ones that involve your research project are about you relating your research project to a stimulus or to another investigation. So when you're assessing your research question, and I know this is one of the things my students will say is that it was really hard to come up with a research question. And it was really hard to come up with the research question because it's really hard to narrow down to a very specific idea. Now, most of you would have done a thing about a research proposal, which is essentially just developing your initial idea. And some people I know have done this as an assessment task. Oh, sorry for that. Apologies for that. I accidentally hit the wrong button. I'll get over here. Here we are. A bit more of that. Okay. Apologies. So, as we said, one of the things there sorry, I've gone too fast there. Your proposal, you would have based your scientific proposal on your literature review. And so your literature review would highlight, here's some areas things that we already know, and here are some areas that we don't know. And so your research to do for your report would focus on the areas that we don't know. You would have also formulated a hypothesis. So your idea is that you think something's going to happen and you prove it one way or the other. And your final scientific hypothesis is what you're going to use your data for. Now, of course, one of the things there, you've also developed a rationale, which is just the reason why you're doing this. So some of you might have said, well, I'm really interested in this area of science, so therefore I want to do some research on it and I want to prove or disprove something based on what we're doing there. You would also have to develop a little bit of a hypothesis or a strategy for doing this. Most of you probably would have been given an end date for your report, and you think, well, if I'm going to finish my report on this time here, I need to develop this here, this here, this here, and this here. Now, this is all stuff that would probably be in your portfolios. Now, whether you're doing that online or doing it as a diary, a diary is just a fine way of doing that as well. And the idea is trying to work out why you've done what you've done there. So your strategy is, I'm going to have my report here at the end. This is what I need to do here. Your methodology is what you've done. One of the most important things in extension is your data analysis. And your data analysis should be supporting what your hypothesis is. And we'll talk a little bit about that a little bit later on there. Is it going to show you, does your data analysis, does your final data support or reject your hypothesis? And of course, communication of the scientific research, and your timelines and your benchmarks, as I said there before. Again, critically analyze the plan. So when you've sort of done a bit of a plan there, do you think you're actually going to be able to do it? Is it possible for you to actually do everything that you want to do there? And critically analyze means, you've got to go in there and really say, this is working well, this isn't working well, and go into a huge amount of depth. Also, you've got one of 3 referencing protocols there. It really doesn't matter how you do that, as long as you've referenced everything appropriately. Now, the next part here, methodology and data collection. Now, this is going to really, how you respond to this is depending on your research. And so a lot of the way that this stuff is being presented here will be quite open, because it's really hard to really respond to that without knowing your exact sort of little thing there. But there are things that you do need to know. You need to be able to respond in your report, and this will come about in your discussion area part of that there as well. And you do need to know the idea of the difference between random errors and systematic errors. And so the idea that random errors in any investigation, particularly in a primary investigation, you're going to get variations in your data. And that's just part of measuring data is. There are going to be these little fluctuations, and hopefully they're not too large there as well. But one of the things in planning your methodology is you have to get rid of and try and eliminate to the best of your ability systematic errors. And so systematic errors usually come from measuring instruments. And so maybe what you're measuring your data with isn't as precise as you thought. You've got to make sure that if you're using measuring devices, that they are zeroed and that they're measuring things accurately. And you've also got to think about, is the data I'm collecting with these, is that what I'm expecting? Now, in a lot of cases there, when you are representing your data as well, one of the common ways of representing data, if you're graphing it, is to use error bars and using a line of best fit there. Now, in this case here, what we've got is a graph that's using error bars, and the line of best fit doesn't, this is the one thing as well, doesn't have to go through necessarily your measurements, but it can, as long as it's represented within the error, then your line of best fit is generally going to be reasonably accurate. Now, one of the things here as well, comparing qualitative and quantitative research, pretty much to do your report, you're going to be using you're going to be using numbers. Qualitative research is really, apologies there. Qualitative research is more in the realm of social science and that there. To do your report, if you're going to answer a hypothesis, if you're going to get apply statistical analysis to your numbers, you need quantitative numbers. You don't need things. Okay, so qualitative, you're saying, well, are people wearing jumpers? Are they doing this? Are people feeling cold? Do people feel happy, sad? And that there are things that it's harder to actually do that. You also have there the idea. Now, some of you may have done this as part of your research. There are a lot of sites out there that you can get things like streaming data and remote sensing. So remote sensing, things like satellite data. The Bureau of Meteorology data is all comes from remote sensing. It means that you can still get quantitative and you can still get primary data, but you get it by using computers and digital technology to get all your data. And so, you know, the probably the earliest ones for that there were satellites. And, you know, the satellites can give you images of areas, and you don't need to go into that area to actually get that data. And streaming is sort of the newer type of data there. Everyone, I think, is familiar with the process of streaming, particularly with the World Wide Web and that there. And streaming data is that you don't just get a data point, like you don't get the average temperature of the day. You can actually go to a streaming data service and get what the temperature is now and now and now. Streaming and remote sensing are essentially usually the same thing. It's just how the data is reported that is the slight difference. And of course, one of the things here as well is that, and this reflects back to your report, you may be asked to, you need to develop a method. Now you may be, and here's particularly with large data sets, if you want to have a look at the Bureau of Meteorology's data, particularly for Sydney, the Sydney city area, you can get data going all the way back to the late 1800s. That's how long data has been collected there. And I think if you can almost get the daily data there, which is thousands and thousands of data points. And this is a really interesting thing, is that if you've got this large sets of data, how do you analyze it? One of the things going, I think last year in the UK, they had a problem that they lost tens of thousands of COVID results because they were using Excel, and Excel has an upper limit of several 100,000 data points or something like that. And no one in the medical system at the time had actually ever used it to that extent. So you've got to be really mindful of that. If you're using particularly large data sets, are you going to be able to use them effectively? Sorry for that. Also, processing data. Now, this is probably one of the harder parts of the course, because one of the things they, particularly in this course, you're asked to do more with the data than you ever have before. Usually when you're doing an investigation in your 2-unit courses, you've just got a couple of parameters and there's an endpoint. You pretty much know what data you're going to get, you know what results you're going to get. But in extension, you're not necessarily going to know exactly how much you're going to get. And so when you're recording your data, and most of you would be recording your data in a spreadsheet such as Excel, Google Sheets, or any other ones there. And you've just got to think about, is it appropriate? And of course, if you're just collecting your data, then it probably is. But how are you recording your data? If you're using remote sensing, does that mean you're just using your physically getting it there, or are you getting a data table in the form of a spreadsheet or a CSV file or something like that? And yeah, is it appropriate? And that's a question you need to ask. You would have at any stage here, and this is not just for your final investigation, but you would have particularly probably early on done a few little experiments to get yourself into the practice of analyzing the data, storing the data, processing the data as well. And I know with a lot of my students as well, often have trouble at the start because you probably haven't used things like Excel and Google Sheets to actually do a lot of that data processing in the past. So that's something that you probably need to practice as well. But you do need to understand that why do you do it this way? Why do you use appropriate digital technologies? Essentially, more than anything else, it's just that it makes it a lot easier to do that. Now, very, very quickly also, you would have conducted investigations for qualitative and quantitative data and things like that. You know, again, you can see there's a little bit of repetition in some of these ideas. But yeah, how do you do that? You would have also probably done some stuff there. This idea, and this is something not necessarily for you to apply to your project, but this idea of what is the impact of making large data sets available? So the LHC, you can go online and you can actually download their results. The Kepler telescope, the Human Genome Project, are all things that have included huge amounts of data. And so you've got to think about what's the impact of that? And particularly with things like the Human Genome Project and the Kepler telescope, is that people can actually now easily analyze that data. So you can go on there and have a look at some of the data about certain gene sequences. And if you know what's going on there, you can actually make guesses about what those genes are going to affect or what they're not going to affect. The idea with these large data sets being made available is that it makes it easier for people outside of the direct project. So people who aren't working at CERN can have a look at the data and make guesses and do so their own data analysis on what that's suggesting. So maybe someone can come up with a brand new, discover a brand new subatomic particle just by looking at the data. There have been cases, there was one last year, or no, the year before, I think, where someone used some of NASA's data to actually discover a planet. And the advantage of this is that science is becoming a little bit more decentralized. The people who make the observations with these large things here can't look at those millions and millions of bits of data, so other people can look at them as well. Now, you would have also done some little things, activities in class where you would have actually gone and looked at those data sets yourself. I know some of my students went in there, looked at these data sets, and then were able to think, well, just wait, this bit of data can link to this data there, and have developed their hypotheses from that. Again, that's an activity you would have done and you would have been able to, and it links very closely to that stuff we just talked about there. Now, one of the things there, we are almost finished this first little section here. There's a few little resources here. Now, if there's other resources in the drive there as well, but these are just some little ones here you can use. Particularly there as well, if you've one of my favorite ones to have a look at data sets is this one here, Gapminder, which is a very visual way of looking at it as well. So particularly if you're still not sure about data, you can actually have some stuff on that as well. And, you can look at a whole range of different things there as well. One of the things here, I know my class have used this, if the statistics sides of things, particularly, it's quite complex. If you just want to refresh your memory on this thing here, Against All Odds, it's actually on ABC iView at the moment, which you can have a look at as well. But other than that, I have been talking very, very quickly for a little bit of time. We've actually finished this first section a little bit early. So yeah, Ian, that's all right. I'll check my email there to get that for you as well. But we're going to start the statistics stuff at 11:30. So if you've got some questions, please ask them here. I'll try and fix up Ian's thing for the moment. If you want to pop some questions up in the chat, but otherwise, if you want to have a little bit of a break, we'll be back at 11:30 to do the statistics stuff. Probably don't log off unless you have to. You can just stay on there and then we'll be back at 11:30, but I'll just sit here for a couple of minutes if there's any extra questions. I know I've gone through things very, very, very quickly. But yeah, by all means ask questions.